So last time I had defined for you the orthogonal groups. So that was over a field F. We had a subgroup ON of F. That was a subgroup of GLN of F, which we viewed as the automorphisms of the vector space F to the n. And this subgroup was the subgroup that had preserved an additional structure, the inner product VW, which was the summation of the coordinates of V, Vi times Wi, I equal 1 to n, because a vector is just in Fn, it's just its coordinate functions. And we saw that if we figured out which matrices were in On of F, these are the matrices A, such that A transpose times A is the identity matrix, or equivalently the matrices A, such that the transpose of A was the inverse of A. And that gave a subgroup of the linear group with some additional nice properties. We also saw from this that this implies that the determinant of A quantity squared is equal to is the determinant of I, which is plus 1. And in a field, there are only two elements whose square is 1. Namely, if you take the polynomial x squared minus 1 is equal to 0, has at most 2 roots, because a polynomial of degree 2 has at most 2 roots. And in fact, this factors as x minus 1 times x plus 1. And the only problem is that you might be in a field where 1 is equal to minus 1. That can happen if you're over the field of 2 elements. But this shows that since the determinant of A satisfies this polynomial, we see that the determinant of A there are only 2 possibilities for it, plus or minus 1. And if minus 1 is not equal to 1, you get both different determinants, and that let us define a subgroup SO N of F as the normal subgroup of ON of F, which had index 2, which is the matrices A such that A transpose is A inverse, and the determinant of A is equal to plus 1. Those are called the special orthogonal group. So that's what we did last time. We showed that this matrix condition was the same as preserving the inner product. And then at the end, I said we're going to specialize this discussion for a while, because it turns out to have beautiful geometric content, to the case where F is equal to the reals. Well, of course, in the real numbers, minus 1 is not equal to plus 1, so we do get a subgroup of index 2. And we notice that if A preserves the inner product, VW, it also preserves the norm, the Euclidean norm. And the Euclidean norm of a vector V is defined as the square root, the positive square root of VV, because this is the square root of the sum of the VI squared, which is the Euclidean distance from the origin. And this is always greater than or equal to 0, whereas in a general field, there's no notion of positivity for this. So this could be 0 for a non-zero vector. You could have the inner product of V with V be 0 for a non-zero vector. Just the sum of the squares of the coordinates could be 0. But in the real numbers, that can't happen. So you get a notion of a norm. And it also preserves the Euclidean angle, which I said is defined by the Cauchy-Schwarz inequality. That's not so important for us, but I'll just write it down. The cosine, the angle between two vectors is defined by this rule. You take their inner product and you divide it by the product of their norms. And that's a number between minus 1 and 1, and that defines a unique angle, and that's the Euclidean angle between the two vectors. So now I'm going to show you what these transformations look like in 2 and 3 dimensions today. What orthogonal and special orthogonal transformations look like. Let me just make one more observation. If V is an eigenvector for a transformation A in ON of F, and this is true over any field, with eigenvalue lambda, i.e., that means that A of V is lambda times V, then lambda squared is equal to 1, i.e., lambda is plus or minus 1. So the only possible eigenvalues are plus or minus 1 for an orthogonal transformation. And that's because you use the fact that an eigenvector for this with eigenvalue lambda, and, sorry, I have to say this too, and VV is not equal to 0. So if it's an eigenvector which has a non-trivial inner product with itself, which is certainly true over the real numbers because of this property, then lambda is plus or minus 1, because we write down that VV is equal to AV. That's because A is an orthogonal transformation. And AV is lambda V both times, so this is lambda V. And then we use the fact that this inner product is linear in each variable. See, if I scale V by lambda, I scale this inner product by lambda. And if I scale W by lambda, I also scale the inner product by lambda. So I pull out a lambda squared. And if VV is non-zero, I can divide both sides by it. This is an equality that takes place in the field F. Now divide by VV, which is not equal to 0, to get 1 is equal to lambda squared. And so the eigenvalue on a vector, if the eigenvector has a non-trivial inner product with itself, is equal to plus or minus 1. That's certainly true over the real numbers. So we're going to use that. That if we have an eigenvalue, it has to be plus or minus 1. Of course, you needn't have an eigenvalue. So we've already seen transformations that don't have eigenvalues, and I'm going to show them to you in a moment. Right now, in fact. Let's take a look at the group SO2. Do transformations A in SO2 look like? We're going to do SO2, and then we're going to do its non-trivial coset in O2. Well, here's the plane. It's acting on the plane. The plane has two standard basis vectors. We'll call them E1 and E2. So E1 is the vector 1, 0, and E2 is the vector 0, 1. And they have the property that their lengths are 1 under this inner product, and that the angle between them is 0, namely they're orthogonal to each other. By the way, we see that theta is equal to pi over 2, so 90 degrees, so the vectors are orthogonal if and only if VW is equal to 0, if and only if V is orthogonal to W. So orthogonality just means that the inner product is 0, and if you take the inner product of these vectors, you get 1, 0 plus 1, 0, so you get 0. So they're orthogonal vectors of length 1. So where does A of E1? Well, A of E1 has to lie on this circle somewhere, right? Because it has to be a vector of length 1. So wherever it lies in the plane, it's on that circle. So, yeah, Atticus.
Why does A of E1 have
Because A is an orthogonal transformation. Orthogonal transformations preserve the inner product, so they preserve the norm of the vector, which is the inner product of a vector with itself. These vectors both have norm 1. So we know that A of E1 has to be 1, A of E2 has to be 1, and A of E1 has to be orthogonal to A of E2. Right? If we're preserving lengths and angles. So A of E1 is somewhere here. Let's put it right there. Some vector on the circle. Now we can describe a vector on the circle by the angle it subtends from E1. This would be the vector which would be cosine theta, sine of theta. Right? Once I know the angle between 0 and 2 pi, I can describe the coordinates of this, right? By x and y coordinate. Now where is A of E2? Well, we don't know yet. But A of E2 has to be orthogonal to A of E1. And there's a unique line that runs orthogonal to this vector. Right? And A of E2 has to also have length 1. So there are only two possibilities for it. It could be this vector, or it could be that vector. Okay, now this vector happens to be the vector in coordinates when you work it out. You see, what I've done is it's the cosine of theta plus 90 degrees, sine of theta plus 90 degrees. So the coordinates would be cosine of theta plus 90, sine of theta plus 90. Of course, that's what I'm doing. I'm adding 90 degrees to theta. And when you work that out, that's minus the sine of theta, cosine of theta. Whereas this vector is minus that. Correct? So this vector would be sine of theta minus the cosine of theta. Well, which one is it? Which one is it? Well, I can tell you which one it is in the following way. Because I have one more condition on A. Besides that it takes E1 and E2 to vectors of length 1, which are orthogonal, I know that the determinant of A has to be equal to 1. Because I assumed it was an SO2, not an O2. Okay, since the determinant of A is equal to 1, I can try to write down the matrix of A from where I know it takes the basis vectors. Remember, the first column is A of E1, and the second column is A of E2. So the first column I know is cosine theta, sine theta. And then I can put these vectors in the second column and see which one gives me determinant 1. See, they're negative of each other. So one will give determinant 1, one will give determinant minus 1. Because if I change the signs in the second column, that changes the determinant by minus 1. So let's try the first one, that one over there. I get minus sine of theta, cosine theta. And miraculously, that has determinant 1. Because the determinant is cosine squared plus sine squared. So that has to be A of E2. We can forget about this one. That one gives determinant minus 1. This one is A of E2. And what is the transformation A doing? Well, once I know what it does to E1 and E2, I can determine on anything. And you'll see that what it does is it simply takes a vector V and it rotates it through an angle of theta. Once you know A of E1 and A of E2, you can figure this out. So this is nothing but the rotation through an angle theta. Could write it that way. And that's the most general transformation in SO2 because we didn't do anything special. We just figured out where it took E1, that rotated it through an angle of theta, and then because it has to preserve all these properties and have determinant 1, it turns out it rotates everything through an angle theta. Namely, this A of E2 is just rotating it through an angle theta here. And how do we compose transformations? Well, it turns out when you multiply these matrices and you use the laws of sines and cosines, you'll find that the composition of the rotation through the angle of theta with the rotation through the angle of phi is equal to the rotation through the angle theta plus phi. Well, that's obvious from geometric considerations. If the first transformation rotates through theta and the second transformation rotates through phi, then the combination is rotating through the sum of the angles. So in particular, we have an isomorphism here between two groups that you know. So we get an isomorphism of groups. It turns out abelian groups between SO2, I'm going to call it F, and the set of Z in the complex numbers such that the absolute value of Z is equal to 1 under multiplication of complex numbers that takes a transformation here, A, which is the rotation through the angle theta, and it takes it to the corresponding complex number on the unit circle, Z is equal to e to the I theta. Because when I multiply two rotations, I add the angle, which is the same as multiplying these two complex numbers of absolute value 1. Or you could say that this Z is just what F is of E1. So that the entire transformation is determined by what it does to the first basis vector. Now, that's the rotations. That's the rotations. You get a very simple abelian group. But O2 is not an abelian group. So that's a little warning. Not abelian. But what's very cool is that anything in the non-trivial coset of SO2 is a very simple transformation. So now, what are the transformations A in O2 minus SO2? There's another, this group has two cosets, right? Here's O2. Here's the subgroup SO2. We now know that they're all rotations by an angle theta. What's in the non-trivial coset? What are the things that have determinant minus 1?
All the transformations where you take A2 the opposite way.
Of course. That's one way of saying it. Namely, we do a rotation, and instead of taking E2 to this vector, we take it to that vector. Very good. And that's perfectly good coset. But I'm going to describe them in a more simple way. Where, see this, we sort of privileged this basis E1 and E2, and we said where they went. And we remember from our general linear algebra principles that sometimes we might want to view a transformation from the point of view of a different basis to take advantage of its eigenvalues. Now, when does something here have eigenvalues? When does an element in SO2 have an eigenvector? Yeah, Atticus.
When the determinant of A minus I is equal to 0?
Well, that would be an eigenvalue of 1. It could also have an eigenvalue of minus 1. Right? That's right. But which of these, we know everything now in SO2. They're all rotations. When does a rotation have an eigenvector? Emily.
The angle of 0 or pi.
Exactly. There are only two elements in SO2 that have eigenvectors. You can have the trivial element. Rotation through the angle 0 has matrix +1, 0, 0. And rotation through the angle pi is the matrix -1, 0, 0. And so they both have eigenvectors. And the eigenvectors are E1 and E2. And the first one, the eigenvalues are +1. And the second one, the rotation takes E1 to minus E1, and it takes E2 to minus E2, so it preserves these two lines. Good? In fact, everything's an eigenvector for these things, because they're just scalar matrices. However, when we go over here, I claim that each such A has two orthogonal eigenvectors. Every such transformation has orthogonal eigenvectors, V1, V2. And V1 has the property that A of V1 is equal to V1. And V2 has the property that A of V2 is equal to minus V2. So that if we looked at the matrix of this with respect to those two vectors, it would look like this. But that's a matrix with respect to a different basis. Not E1 and E2, but V1 and V2. So I have to prove that to you. That even though rotations may not have any eigenvectors, the only possibility for rotation is either everything is an eigenvector or nothing is an eigenvector. The things that are in this non-trivial coset are going to have distinguished lines that are eigenvectors, one which is a +1, one which is a -1. Okay, let's prove it. Consider the characteristic polynomial. That's what we always do when we look for eigenvalues and eigenvectors. Look at the characteristic polynomial. Proof. The characteristic polynomial of A looks like x squared minus the trace of ax, and then it's plus the determinant of A, which is -1. We don't know what the trace is, but we know what the determinant is. That's what it means to be in this non-trivial coset. It means the determinant of A is -1. Now, this is a quadratic polynomial. Its roots over the real numbers tell us what the eigenvalues are, right? It may not have any roots over the real numbers, like in these cases, right? However, in this case, I claim it has both roots in the real numbers. Because if it didn't, its roots would be complex conjugate. Conjugate in the complex numbers. Because if you have a polynomial with real coefficients, either it has two roots that are real or its roots are complex conjugate. Otherwise, the sum of the roots can't be a real number and the product of the roots can't be a real number. I mean, use the quadratic formula. Okay? The roots are z is equal to minus b plus or minus the square root of b squared minus 4ac over 2. If this number is positive, you get two real roots. And if this number is negative, you get two complex conjugate roots. Okay? Now, this number here, but the determinant would be the product of the two roots. So it would be z times z bar. And what do we know about the product of a number, complex number by its conjugate? It's positive. Good. But on the other hand, the determinant of A was assumed to be minus 1. So therefore, we get a contradiction. Implies the two roots are real. Let's call them lambda 1 and lambda 2 are real. And their product is equal to minus 1. This term here. But every root of the characteristic polynomial gives an eigenvalue for the transformation. Remember we showed that? And we showed the only possible eigenvalues for an orthogonal transformation are plus or minus 1. These are eigenvalues for A. So, so lambda 1 is equal to plus or minus 1. And lambda 2 is equal to plus or minus 1. On the other hand, their product is minus 1. So one of the roots must be plus 1, and the other root must be minus 1. So far, so good? That gives us two eigenvectors, v1 and v2, of this sort. Okay? And all you have to check, and I'm going to leave this to you because it's an amusing check, is that they're orthogonal to each other. That's the one thing we haven't checked, that the two eigenvectors, if they're not orthogonal to each other, it's not an orthogonal transformation. Okay? So what does a transformation look like? Well, it looks completely different than this, or even this idea of rotating and then taking the second vector down to here. What it looks like is this. You find the eigenvector with eigenvalue plus 1. You find v1. There's no harm in normalizing, by the way. Why don't we normalize our vector v1 to have length 1? You can always, once you have an eigenvector, you can scale it to have length 1. Likewise, why don't we organize our second eigenvector v2 to have length 1? So we find our first eigenvector that has length 1. Then v2 has to be orthogonal to v1, so lies here. It could be anywhere on that line. And what happens here is that v2 is taken across the line to minus v2, and v1 is fixed. So this line is fixed by the transformation, which therefore fixes the line orthogonal to it, because it preserves orthogonality. v2 lies on that line and is flipped over here. By the way, here let me give you a proof that v1 is orthogonal to v2. I don't want to kill you. Apply A. This number has to equal this number. But this number is v1 minus v2 by the fact that they're eigenvectors. Correct? And by the linearity in the second variable, this is minus v1, v2. So this is some real number which is minus itself. Therefore, it's 0. Therefore, the vectors have to be orthogonal. Eigenvectors. So we have this vector v1. v2 has to lie on the line orthogonal to v1 and is flipped by the transformation like that. Once I know what happens to v1 and v2, I know what happens to anything. And what this transformation does is it simply reflects in the line orthogonal to the line v1. Around the line v1. But v1, so v1 determines the transformation. Once you know the eigenvector or the line which is fixed by this transformation, and there must be such a line fixed because we just proved there has to be an eigenvalue of 1, then the entire transformation is done by taking a reflection around that plane. And that has order 2, right? If I square that transformation, I get 1. So every element in this non-trivial coset has order 2. However, they don't commute with each other. And that's where the non-commutativity of this group comes in. Because if you reflect around the line v1, and then you reflect around the line v2, you get a rotation. You get a rotation that has to do with the angle between the lines v1 and v2. Right, exactly. So you should check that reflection around v1 composed with reflection around v2 is the rotation through some angle theta, because it has to be. This has determinant -1. This has determinant -1. So the determinant of the product is +1. Figure out what theta is in terms of v1 and v2. And you'll see that the reflections don't necessarily commute with each other. So here we have a geometric description of every transformation in the group O2. In this subgroup, it's rotation around the origin of some angle. And in this non-trivial coset, the elements have order 2. They're reflections around some line. And never mind. So we're going to do this for more complicated orthogonal groups, but you should at least see this in dimension 2. Let me push this argument a little harder in dimension 3. So in dimension 2, we saw that everything in the non-trivial coset had an eigenvalue of +1. So here's a great theorem that was first discovered by Euler, the leading mathematician of the 18th century. Euler's theorem. Any A in SO3 has an eigenvalue of +1. So there is a V in R3 such that AV is equal to V. Yeah?
Let me state this without matrices.
They had a notion, which we're going to get to, of what a rigid motion was. Something preserving distance and things of that nature. And so without matrices, what he said was, if you had a motion of R3, some transformation that took R3 to itself, there you didn't need what groups were or anything like that. And it preserved the origin, and it preserved the sphere. It preserved distance from the origin. Then it had to have what's called an axis. It had to have a fixed vector. We're going to see what I mean by an axis. So any motion preserving the sphere S2 in R3 has an axis. That's how it's stated by Euler. You're going to see what an axis looks like. An axis of rotation. An axis of rotation. Proof. Again, if we want to prove an eigenvalue, what do we look for? What do we look at? We want to look at the characteristic polynomial and see where its roots are. Now the characteristic polynomial has degree 3. So if we factor it in the complex numbers, it looks like this. So 3 roots in the complex numbers. One possibility. They're all real. A second possibility. There's one real root and two complex conjugate roots. Any other possibilities? No. You say no. Why you say no? Why do we have to have a real root for a polynomial of degree 3? The complex roots come in pairs. Good. So it's because it's of odd degree. A polynomial of odd degree always has a root over the reals. The proof? The intermediate value theorem. If it has odd degree over the reals and you look at it for a very negative value, the value of f is down here. It's negative because it starts off with x to the odd plus higher terms. And this starts to dominate. And so if you take a negative number to an odd power, you get a very negative number. So for very negative x, it's down here. For very positive x, it's up here. So the intermediate value theorem says sooner or later it has to cross the x-axis. That's it. That's the proof. It's by calculus. It's an unusual property of the real numbers. You expressed it in terms of the complex numbers, which we happen to know a little bit more about. But even if we knew nothing about the complex numbers at all, a real polynomial of odd degree has a root. Whereas of even degree, no such thing. X squared plus 1 has no real root. But don't think it's anything miraculous of odd degree. If we didn't have the intermediate value theorem, it's like false for the rational numbers. X cubed minus 2 has no root in the rational numbers. It's because there's room here. But over the real numbers, by the intermediate value theorem, the most useful theorem in calculus, we have a real root. OK. So therefore, we either have all three roots real or one real root and two complex conjugates. If we have one real root, we know the product of these two numbers is positive, and the product of all three of them has to be the determinant, which is 1, by our hypothesis that we're in SO3. OK? So if these two have a positive product, this thing has to be positive. Since it's plus or minus 1, it has to be plus 1. Because any root is an eigenvalue. Over here, we have three things which are all plus or minus 1. And the product of them is 1. So they can't all be minus 1. Agreed? So therefore, in this case, at least one of them has to be plus 1. In this case, this one has to be plus 1. Therefore, we have an eigenvalue of plus 1. Therefore, we have a vector that's fixed. Very cool argument. Euler didn't have the fundamental theorem of algebra to play with, but he figured this out. OK. What does this mean geometrically? Well, let's take a look at the case of 3 space here. And then we'll see what I mean by when we re-express Euler's theorem. Here we're now in 3 space. And the transformation preserves the sphere in 3 space. Because it preserves the vectors of distance 1 from the origin. That's not the greatest sphere, but you're going to imagine it. OK? Now, let's take the eigenvalue for this transformation. The eigenvalue need not be one of these unit vectors, God forbid. The eigenvalue is some point that comes up here and hits the sphere here. There's our eigenvector. And so if we draw that line through the origin, it meets the sphere in 2 points. And those points are fixed by the transformation. What does the rest of the transformation do? What does the rest of the transformation do? These are the fixed points. Next claim is that A preserves the plane orthogonal to V. In other words, there's a plane through the origin here which is orthogonal to this vector. Even worse drawing, right? But everyone can see that. Namely, let me just draw the sphere without the coordinate axes, because I'll do a little bit better. Here's the vector v. Well, let's put v at the North Pole. Why not? here's the vector minus v on the south pole, and it preserves this plane that cuts orthogonally to the sphere. So in particular, it preserves the intersection of that plane with the sphere, which is this equator. Why? Because if VW is equal to 0, then this is equal to AW, which is equal to V times AW, because V is an eigenvector. A preserves the inner product. So if W is orthogonal to V, so is A of W. So if you're in the plane orthogonal to the eigenvector, you stay in that plane. Okay? It also preserves, why just do it preserves the vectors of a fixed angle. So it in particular preserves all well, we'll go for that for a second. So it does something in this plane. What does it do? Well, let's take a look at the matrix of A. The matrix of A looks like this. Here's the vector V, 1, 0, 0. And here we extend our basis to be an orthogonal basis for the plane orthogonal. So let's take E1 and E2. It's a basis for the plane orthogonal to V. Well, I claim that the matrix now looks like this. A little 2 by 2 matrix there. Because to say that it preserves the plane means that when you apply A to E1 and E2, you get linear combinations of E1 and E2. It doesn't involve V. What does this thing look like? Well, this is a linear transformation which has to be equal to its own transpose. Its transpose is its inverse. Namely, this is an orthogonal transformation of the plane orthogonal to V. Orthogonal transformation of the plane spanned by E1 and E2, because otherwise you wouldn't get an orthogonal matrix A. Namely, if it preserves the inner product on 3 space, it certainly preserves the inner product of vectors in this plane. Good? Now, what do we know about the determinant of this orthogonal transformation? It's 1, because the determinant of A has to be 1. A is an element in SO3. We have a 1 up here, so the determinant of this orthogonal with determinant equal to plus 1. Namely, this is an element in SO2 of the orthogonal plane. And we know all the elements in SO2. What are the elements in SO2? We just did those. That's a rotation through some angle in the orthogonal plane. So in this orthogonal plane to V, here's E1 and E2. Shouldn't think that's, E2. What's happening in this plane is we're rotating through some angle theta. And that's how it preserves this circle. It just rotates this circle around through an angle of theta. And in fact, once you have that, so I write this down. So the transformation looks like this. There's some vector that it fixes, and in the orthogonal plane, you get the rotation through an angle theta. And what that has the effect of doing on 3 space, when you work it out, is it just rotates the sphere around through an angle theta. So it preserves all these circles like this that are perpendicular to that plane. All the, what are these things called? These are degrees of latitude. The fixed degrees of latitude are preserved, and in each little circle it just rotates it around by an angle of theta. So the sphere is just, so that's what this is about. Every preserving S2 has an axis of rotation. Namely, there's some fixed line through the sphere so that the motion consists of just turning by an angle of theta around that fixed line. That's Euler's theorem. However, the line depends on the transformation. So again, if you have 2 such things, this is non-commutative group. If you have 2 such things, they have different axes. So what happens if you compose a rotation around one axis with a rotation around another axis? Well, you have to get a rotation around a third axis, right? Because anything in this group is a rotation around an axis. So that becomes an interesting problem, which Euler worked out. How do you compose 2 different axes of rotations? But for any individual transformation, you have this picture. Cool? Very cool. Okay. Now, I mentioned the word rigid motion, and I'm just going to end with that because that's another thing we're going to study. Now, these are linear transformations. In particular, they fix the origin. But people were interested, when they studied Euclidean geometry, of all motions of the plane or of three space, etc., that would preserve the notions of Euclidean geometry, that would take congruent triangles into congruent triangles, preserve length and angle. So you might study all motions or all transformations, except I don't want to use the word transformation because it sounds like a linear transformation, from Rn to Rn, which preserve the distance d of VW between 2 points. So d of VW is by definition the norm of v minus w. You take the difference vector and you take its distance from the origin, right? Here we are. Here's v. Here's w. If you want to calculate the distance here, you take the difference vector, which is this vector. I don't know what that is, w minus v, and you take its length. That would be the distance between that point and that point. And that's called the group of rigid motions. Now, the group G of rigid motions contains the orthogonal group. And in fact, the orthogonal group is just the group of rigid motions that preserves the origin. Claim: if M is a rigid motion and M of the origin is the origin, and you certainly need that to be a linear transformation, then M is equal to A is a linear transformation in ON. That's an amazing fact. Let's see, in some sense, why it's true. Let's see at least that it preserves distance. A of v, without knowing it's linear, we can at least show that A of v, A of w is the inner product of v with w. Well, let's expand this thing out. V minus w, let's square it. That's the inner product of v minus w with v minus w. It becomes the inner product of v with v, which is v squared, plus the inner product of w with w, which is w squared, minus 2 vw. Okay? Now, my rigid motion preserves this, the distance between 2 points. If it also preserves the origin, it preserves the distance between a point and the origin, which is this, or this. So if my transformation preserves the distance between 2 points, and it also preserves the origin, it preserves this quantity, and this quantity, so it has to preserve that quantity. And that shows that it preserves the inner product. Doesn't yet show it's linear, but it shows that it preserves the inner product. Hold off on the linearity for the moment. Hold off on the linearity for the moment.
Professor Gross, before you erase that,
Yes?
what you've written on the right side there seems to indicate that any motion preserving the unit sphere is an SO3 on the right board. Is that true?
Here?
Yeah.
Over here?
No, where you wrote Euler's statement of...
Oh, no. Any motion preserving S2 with determinant 1. Sorry. Otherwise, sorry, Euler also knew the determinant. I'm sorry, because there are also orthogonal transformations that preserve. An example of an orthogonal transformation, a 3-space, that preserves S2, but does not have an axis of rotation, is the transformation this, -1, -1, -1. That has the effect of taking every point to its antipodal point on the sphere. That's a perfectly good transformation of R3 that preserves the 2-sphere, but has no axis. It's only the things of determinant 1. I'm sorry, I should have put that in, because that's a critical condition in our proof.
It has determinant minus 1, it's not a rigid motion. Or
Oh, yeah, it's an orthogonal transformation. It just has determinant -1. This only applies to the subgroup SO3. Remember, in two-dimensional space, first we classified what was in SO2. Then we classified what was in the non-trivial coset. Correct? So here, we're only classifying what's in the subgroup. We're not saying about what happens when you have determinant -1. Okay? Yeah?
So did others say that direction was preserved? Or how did you-
Oh, it was called orientation preserving motion. So this determinant 1 was called orientation preserving. There's a notion of orientation where you had a right-hand rule and a left-hand rule. Those of you who've done chemistry. So it was any motion of three space, preserving the origin, preserving orientation, had an axis. In any case, here at least I show you that if you have a rigid motion that preserves the origin, it preserves the inner product. So it's reasonable to think it's in ON. I still have to show you it's linear. Okay? And in particular, anything in ON is in this group of rigid motions. Is a subgroup of the group G preserving the origin. So I'm going to give you some other things that are in G. Another subgroup of G. Translations. A fixed vector B. In other words, let's call that T of B of a vector V is equal to V plus B. You add B to any vector. Now that clearly preserves the distance between 2 points, because the distance between T of B, V, the distance between TB of V and TB of W is the norm of the difference vectors, which is the norm of V plus B minus W plus B. The vector B cancels out of this, so it's just the norm of V minus W, which is just our distance between V and W. So if you just shift the plane along by a vector, you're not changing any distances. Now that clearly doesn't preserve the origin. And that group is isomorphic to the group Rn under addition. Because if you compose the transformation of B with the translation by the vector B prime, you get translation by the vector B plus B prime. So here we have a nice abelian subgroup that just translates things along. Here we have a group that's quite complicated, that preserves the origin and moves things around, but preserves distance. And I claim that that's it. That's it. That once you show, and we haven't yet shown, that ON is a subgroup of G preserving the origin, because we haven't yet shown that if you preserve the origin and you preserve length, you get linear. But if you believe that, then I claim that G is the product of those two groups, ON times Rn. Every element in G is uniquely an orthogonal transformation composed with a translation, and that this subgroup is actually a normal subgroup. So that any rigid motion of a vector has the form AV plus B, where A is an orthogonal transformation and B is a translation. So that by studying orthogonal transformations, we almost get the entire group of transformations that preserve distance. And that's what you want to study when you want to study Euclidean geometry, the group of transformations that preserve distance. So let's prove this, and then I'll come back next time with the proof of linearity. Okay? Here's the proof. Let's think. We have an arbitrary motion. It takes the origin somewhere. Okay? If I only could take the origin to itself, I could apply this. How do I get to a transformation that takes the origin to itself? Very good. It takes, my arbitrary transformation has the property that m of 0 is some vector v in Rn. Say, all right, consider the transformation t of minus b composed with m. That takes the origin to itself, because this takes the origin to b, and then I translate by minus b, and I get back to 0. So t of minus b composed with m is an orthogonal transformation. So m is the product of t of b with a. So it's every element in the thing is of the form an element in the orthogonal group and an element which is a translation. Okay? So you get the group by putting together these two subgroups. This turns out to be normal. This turns out to be isomorphic to the quotient group. Now, where are we going? Because this is a reasonable question. We've just built up an interesting geometric group, the group of motions. We're not quite done with it, but we're almost there. Now, what we're going to study is the various nice forms for elements in this more complicated group. I've given you nice forms for elements in SO2 and SO3, where you have an axis or you have a line around which you reflect. These are slightly more complicated things, so we're going to have several different canonical forms for elements in this group to analyze the symmetries of space that are preserved by them. And then, and this is totally cool, we're going to analyze finite subgroups and discrete subgroups of these groups that give beautiful tessellations of space, dividing up space into various pieces. And as I said, there's a current model of the universe that's going on, not with a finite subgroup of this group. Well, close. It's a finite subgroup G in SO4. In fact, the alternating group on 5 letters. This little picture is now being used to model the universe. So I'll discuss that a little with you when we get there. That's where we're heading in the next couple of lectures.